Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast.
Welcome to another episode of Lost in Science. It is another half an hour of science. My name is Chris, and look, as you all know, I'm a bit of an extreme sports fan.
Oh, yeah.
Oh,
Yep.
yeah?
The most extreme.
That's
Yeah.
sort of news
The
to
extremist.
Oh, yeah, look,
Chris.
it's you probably wouldn't have noticed because
Danger.
it's not really
Chris
obvious. I know,
Danger
yeah, that's right.
Lassig. That's you.
That's true. So, yeah, of course, I was really interested when we had recently a bloke in America jumped out of a plane without a parachute
Yeah, I
and
heard
landed
about that.
safely. Yeah. So
In a net.
In a
He's
net of
crazy.
all things.
Yeah.
Yeah. So he said in his, in one of his interviews that, look, it's just do the maths, do the physics. It's all fine. And so I thought, we're a science program. Let's do the maths. And
jeez, yeah.
we're going to look and see how it actually wasn't that difficult.
The speed at which I splatter
Yeah.
against the sidewalk. Like, yep, do the math.
Yeah, something like that. Manisha, what have you got for us?
I'm going to be talking about speed stuff too, and how quickly the tectonic plates are moving, and in particular Australia and where we're going.
Oh,
All the places we are traveling.
Yeah. So everyone's going on a holiday.
Yeah, we're going on a really
and
long
forced
trip.
holiday.
Oh, well, that's really interesting. You guys are talking about sport and
Movement.
speed and movement, because in the lead up to the Rio Olympics, I thought I would talk a little bit about, or maybe just investigate a little bit about what the hell is going on with all the drug cheats.
Ooh.
And especially, because there's news recently about Russia, the athletics team, being kicked out because they are
Being sneaky.
being drug cheats.
Yep.
Being drug cheats.
So yeah, and so how do they do it, and how do they get away with it, and what's the science of it, and what does that actually do? So I'm going to be talking to
interesting.
Dr. Oliver Jones, who's a lecturer in applied chemistry and has some really interesting stories about drugs in sport.
Right.
So I'm going to be talking a little bit to him
Cool.
about that. Yeah. Anything?
Okay, speed, movement, earth-shattering. That is Lost in Science for this week.
Yay.
On with the show. Yes, you're listening to Lost in Science. My name is Chris, and I am talking about Daredevil, I guess we can say that, Luke Aikens, who skydove from 7.6 kilometres and landed safely without a parachute
7.6 kilometers.
in a net. Yeah, 7.6 kilometres. I've been trying to find out why he actually went that high. I have some ideas. I haven't been able to get a good answer on that, because that is quite high for a skydive.
What?
Was he trying to break a record? Is that why he went
I
so
think
high?
the fact that he skydove without a parachute.
Yeah, that was
breaking
pretty
the
much
record.
the
So,
record, yeah.
but couldn't he have done that at a couple of kilometres?
Yeah.
No one's ever done that before.
I'm not sure, because to me it didn't make much sense, because he has to obviously hit his net. But maybe it's the reason is like there was some controversy beforehand where they're going to let him actually jump without a parachute at all, whether he had to have like a parachute for emergency purposes, which is going to off his whole balance and this kind of thing. Then they allowed him to get away with that because of the height. So it's quite possibly that if it was lowered down, maybe there's less time to fix something that goes wrong, or because he jumped out with some helpers who had parachutes, and maybe the idea was that if something went wrong with him, that they could grab him, and I don't know. I'm not sure what the reason is. I will research that. I'll try and get an answer. Anyway, so yeah, he jumped out of a plane without a parachute. This is like the remarkable thing. We shouldn't perhaps ignore that simple fact. But look, when you look into the what actually happened there, the science of it, if you will, it doesn't become that remarkable, because after all, it is not the fall that kills you. It's the sudden stop at the end, and so it's managing that sudden stop that is the key part. So he was moving quite fast when he was falling, quite clearly. He was moving at the aptly named terminal velocity. Terminal velocity, you know what that is?
Yes.
What is that?
Very fast. Very fast movement downwards.
It is, but why is it terminal?
Is it like the fastest you can go?
Yeah.
Yeah.
So it's when the force of gravity that's
I
pulling
know
you down
things.
it balances out against the drag force from the air pushing back up. So for a human doing that kind of spread eagle skydive thing, it's around about 200 kilometers an hour, roughly.
Oi, mama. I would not want to be heading towards the Earth at 200 kilometers an hour without a parachute.
No, well... Yeah, we'll get to that. We'll get to that.
Especially if he's only got 7 of those kilometres.
Oh my God.
Work with.
It took a couple of minutes for him to get down there. What? But yeah, so 200 kilometres an hour he's going roughly. Actually 193 kilometres specifically is what they've reported that he was moving at. I mean, it is possible to go fast if you pull your arms in and you dive straight down.
We call that pin jumping.
Pin jumping, do we?
I don't know. You know when you dive off a diving board and you just do a pin jump?
I thought it was a pencil.
Oh, it's a pencil jump.
Maybe.
I don't know. Don't ask me things.
You might remember Felix Baumgartner, the other bloke who jumped off a very high balloon and broke the sound barrier for going fast enough.
Oh,
so,
wow.
yeah. So it is possible to make yourself go faster by pulling your arms and being streamlined. But generally, if you're kind of spread-eagled, the way the wind will get you get about 200 kilometres an hour. So, yeah. Now, as I said, it's the sudden stop at the end, though, not the speed in particular. It's how quickly you decelerate. So the faster you decelerate, the more stress is going to be on your body and the more damage is going to be done. In terms of their speed itself, we know that, for instance, getting hit by a hard object, say a car, at about 50 kilometres an hour is enough to do a lot of damage to you. But we have now ways of slowing down that impact. When you're a passenger in a car, you have things like the crumple zones and you have airbags to make sure you don't come to a sudden stop. It absorbs the impact and makes your deceleration is reduced. And so it is possible to survive collisions at higher speeds. So we have the technology. In principle, it should be possible. So
you want to be able to slow down over a long period of time.
That's right. Yes, right. Now, so we're going to do some maths to try and figure out what exactly happened here. Now, the maths isn't terribly complicated, but we're doing it over the radio. So, this could be interesting.
Pens and paper. Oh.
And if you're driving, just visualize.
Yeah, just visualize.
Just visualize. Don't visualize crashing.
Okay. So, like I said, he was moving 193 kilometres an hour, which is 53.6 metres per second. We'll convert everything to metres and seconds because it's easier. Okay?
53 I will take your word for that.
Yep. Now,
it's faster than Usain Bolt, isn't it?
It is a bit, yeah. He's not
just on the Olympics theme.
He's not falling that fast. If he might have a plane, though, he'd probably go as fast. Anyway, so now the deceleration that they aimed for with this, and they reported roughly, was about 3.9 G. Mm-hmm. Now, G being the acceleration due to gravity, which is 9.8 metres per second. So this makes 3.9 G is the acceleration or the deceleration, like the negative acceleration that was slowing him down. Now 3.9 G, I don't know whether that sounds like a lot or not. Apparently, when a parachute opens, it's about 3.5 G. 3.5 G is the force from that. Things like fighter pilots routinely experience like 9 G. So 3.9 G
can survive up to about 15.
Yeah, so 3.9 shouldn't be too bad. So that, when you go 3.9 times 9.8, which was the G, you get about 38 metres per second was the deceleration. So to work out the time, then we just take his initial speed, 53.6 metres per second, divided by the deceleration of 38, and we get 1.4 seconds is the time it took for him to stop.
Oh, that's real quick.
It is pretty quick, but it was giving you 3.9 G, which again isn't too bad on you.
Yeah.
And now to work out the distance that you move in that time, that gets a bit more complicated. You have to remember your formula for high school. If you have an acceleration of A or A, and you have a time of T, then the distance you move at the constant acceleration is a half AT squared. Trust me, you can write this down on your piece of paper if you've got that out. So we just plug our numbers in, and with our deceleration of 38 metres per second and the time 1.4 seconds, the distance you would move over that time is 37 metres.
Of course it is. 37 metres. I did that math in my head.
So what they did was they used a big net that was 60 metres above the ground, so there was room for error, and basically he came to a nice, gentle stop over that 37 metres.
Wow.
So the maths, when you actually sit down, isn't actually that bad. As long as you have a big enough net, you have enough time to slow down, that 1.4 seconds is all you need, then you can survive it. And indeed he did.
A big enough net and also a
high
net
enough
Well, high enough, and also it's
Strong
under
enough.
you.
It's also strong.
yeah.
Yeah,
In
yeah.
the
You
right
have to hit the
position.
net. You do have to hit the net. It was a very strong net, of course. It was made of ultra-high molecular weight polyethylene,
Of course it was.
which is like a type of plastic with really long polymer chains, so it makes
Cool.
it really strong. So yeah, it's very strong. Doesn't stretch though. So the actual cushioning was done by these kind of apparatus with air cylinders. So the net kind of collapsed on it, and they pulled down these air cylinders, gave the compression that helped him slide down. Apparently, it's the thing they use in Hollywood all the time, as you know, your Hollywood stunts. So look, it's actually straightforward. The technology is straightforward. You just needed the big enough net, and yeah, like you said, you needed to hit the net. Their initial plan, when this was first proposed to him, the makers of the television program, because it was done for on TV, they wanted to use a slide. They suggested a 800-foot slide, which is about 240 meters, and so you would have to hit the slide and the slide down to a stop. He said no to that, but then went away
It's
and
like
thought about how
asking
could we
him
actually
to
do
dive
that.
into like a cup of water or something.
I don't know. It's like,
Why
imagine a
would-
slippery slide, and you're supposed to got to dive down and hit that at the right angle, so you just go
So,
sliding along
yeah.
and gently to a stop.
Imagine the TV, though. It would make great TV.
That would look good. But the net was a much better idea. And as we've seen, it is quite achievable and obviously proved experimentally that was quite achievable.
So, Chris, do you reckon you're going to jump out of a plane without a parachute anytime soon?
I don't think that I could get a net big enough, really. So no, maybe I'll go for the
We
slide.
source you. Oh, yeah, okay.
Yeah. Next episode, I'll do it live on
Oh,
radio. How about I do that?
ooh,
Yeah,
sounds
yeah.
real
Okay, great.
good. Stay tuned for that.
Yeah.
Science, the final frontier. These are the voyages of Lost in Science, our ongoing mission to explain strange new words, to seek out new science and new explanations, to boldly go where no radio has gone before.
Okay, so we all know that the Earth's crust and upper mantle is broken up into tectonic plates. And there's about 7 or 8 major plates, and it's kind of debatable how many plates we have because the definition of a plate is still up for debate.
So these are just like big segments of the crust that move around, like a cracked Easter egg.
Exactly, yes.
Yeah.
Delicious tectonic. So chocolatey.
So nice. So creamy. Yes, exactly. Okay, so in any case, we have 7 or 8 major plates, and then we have many, many minor ones. And Australia sits on the Indo-Australian plate. This plate extends, if you'll believe me, from India to Australia.
Right.
Indo-Australian. So it was formed about 43 million years ago, and it's thought to have been formed when the Indian plate and the Australian plates collided and fused.
So they were separate.
Pardon?
They were separate initially.
They were, or so they fused at one point. So it may not have been like a massive collision, but they were separate at one stage, and then they kind of fused together. And so this happened 43 million years ago, this fusion, but there have been studies that suggest that they actually started to come apart and divide back into 2 or maybe even 3 plates about 3 million years ago. And so when I read this fact, it just got me thinking as to like how all of this stuff happens and what that means for us. So we all know that it's not really unusual for plates to move and for them to shift. There's all that pressure that's building up under the surface, and then the plates shift around, and when the pressure is released, we get things like earthquakes. And if the earthquakes are sort of in the ocean and things like that, we get things like tsunamis and as results of the earthquakes. And typically these tend to occur along the edges of the plates. So places that are situated along the edges tend to experience more earthquakes. So places like Japan or California are more prone to earthquakes because they tend to experience more of that pressure release than other places.
So this is like they talk about the Ring of Fire, which is like around the Pacific. There's is there one big plate with volcanoes and things around that and earthquakes?
Yeah, it's the Pacific Ring.
Okay,
Pacific
yeah.
Ring, is it?
Or it's probably like one of the smaller plates where then all of it's kind of just, it has a lot of those edges, and so there's a lot of that pressure release and the volcanoes and things like that in that area.
And they move around, and this is like why the continents kind of fit together like a jigsaw puzzle because they
so like
joined up.
way back when it was just one massive
Pangea,
sheet.
I think
Yeah.
it was. Yeah.
One massive Pangea sheet, and then that's broken up with all of these pressure, and the continents effectively moved apart. So with these earthquakes and things like that, there were two large earthquakes that happened kind of recently, and this was back in 2012. So I'm not sure if any of you remember this, but there were the two large earthquakes that happened within the Indian Ocean near Indonesia, and these earthquakes were actually they hit much harder than they were expected to hit. So we weren't actually anticipating them to be as bad as they were,
right,
given where we had detected the earthquake coming from.
Okay.
And so a lot of researchers were really intrigued by this, and were really wondering why this earthquake hit so hard. And it actually turned out that the earthquake resulted in a quadruple fault rupture, which means that basically there were 4 existing fractures within the plate. And with the earthquake, with this pressure release, they were just torn apart. And the earthquake was classified as a strike-slip earthquake. So instead of it actually the edges moving up and down, they were pulled apart laterally. So they were opening up. And it was really surprising because this rupture was actually, so instead of occurring along the edges of the plate as it's typically what typically happens when we have earthquakes, it actually occurred in the middle of the plate. So it really suggests that with this lateral opening and with the fact that this is occurring in the middle of the plate, that these two plates are coming apart into the Indian side of it and into the Australian side of it. And so now the Australian side is starting to pull away from the Indian side, and it's actually moving at record speeds. It's the fastest moving continental tectonic plate in the world.
How fast?
So I don't actually know the speed of it, but Australia is shifting northwards 7 centimeters each year, and then shifting to the west 11 centimeters each year. So that
sounds pretty quick.
It is. It's the fastest moving tectonic plate.
Yeah.
Yeah, it's actually that if you think about land mass wise.
You're not impressed, Claire? It explains why I've been walking a bit unsteady lately, I think, falling over a lot.
Yeah, just a bit unsteady.
Unfortunately, that doesn't just because the Australian plate is moving and being quite progressive, unfortunately, our politics in Australia is not keeping up.
Not really as
progressive.
Yeah.
Bam.
Yeah.
Bazinga, I guess. So I think Claire's got a bit on her mind at the moment.
Yeah.
But okay. Anyways, the thing with the Australian plate is that it's actually starting to collide with islands in Southeast Asia, and projections show that the northwest of Australia is actually going to get caught in this collision, and then Australia is going to rotate and then collide against Borneo and South China, and then it's gonna merge with Asia.
This is a very slow moving crash.
Yeah. So I know. Okay, so it sounds
islands scattered everywhere. Yeah.
Yeah, it's gonna be this massive apocalyptic
no.
So many years.
Yeah. Okay. So yeah, I know it might sound scary or scary, but it's gonna take tens of millions of years for it to happen. So I don't really think we have much to worry about.
In the lead up to the Rio Olympics, there's been a lot of talk about drug cheating and performance-enhancing drugs. So to help us see the science through the syringe-filled world of dodgy drug doping, we have a special guest with us today, Dr. Oliver Jones, Senior Lecturer in Analytical Chemistry at RMIT. Welcome to Lost in Science, Ollie.
Oh, thank you very much for having me, Claire.
So, Ollie, with the Russian athletes that have been kicked out of Rio, it seems like drug cheating in elite sports is becoming commonplace now. Is drug cheating a new thing, or is it an old thing?
Certainly not. I mean, you go back to it depends what you call cheating. You see people have been using stimulants and aids to help them run faster or fight longer or whatever since the Roman times and the ancient Greeks.
Really?
Oh, yeah.
Wow. What were they using back in the Roman times?
Well, Roman gladiators would use caffeine, and they'd also use something known as strychnine, which actually is quite a potent toxin, but if you have a small amount of it, it actually acts as a little stimulant. So the idea was to make the fight go a bit longer.
So this isn't a new thing?
Oh, no, not at all. And in fact, even if you look at sports like cycling, they've had a number of drug problems over several years.
Yes. Yep. And it doesn't seem like it's going anywhere.
No, unfortunately it doesn't.
So to get an overview of the state of affairs right now, what, in your opinion, as an analytical chemist, what are the most common types of drugs and doping that's happening in sports, and the types of testing that are currently performed on athletes?
Well, that's a good question. It seems to go in circles. If you go back to the 80s, which is probably one of the earliest Olympics I can remember, it was all steroid hormones and synthetic testosterone and so forth, and nandrolone and various other things. And then it went past that, and we've gone into blood doping, so
Right.
EPO and erythropoietin.
Okay, and there's this sort of, I guess, difference between blood doping and performance-enhancing drugs. Are they similar? Are they different?
Well, it's a sort of yes and no. So it depends how you mean by doping, but the compounds that you might take to increase performance, such as a steroid, are usually external compounds that are not naturally occurring that have an effect in the body. EPO is basically you're using synthetic EPO, which is a hormone that increases blood production. Mm-hmm. So you're trying to stimulate the body's natural production of chemicals to an unnaturally high level. Okay,
Right.
so that makes it harder to track, because how do you know that it's not just a naturally high level?
Right, and that's quite common these days, isn't it? The EPO.
EPO seems to be it's going down a little bit because testing's got better for it. But if you look at Lance Armstrong, for example, EPO was one of the things he was alleged to have taken.
Right.
And it seems to have been endemic in cycling, in particular, for a fairly long period of time.
Yeah. I guess it's one of those things that as soon as the testing catches up, then the amount of drug that you see coming through as positive results goes down, because, it's one of those, or they're always chasing their tail with the testing and the...
Oh, yes, you
the
see new things come in as tests develop for the old things. So, for example, EPO sort of fallen off a bit, and now we've got the peptides in the footballers. And they're another thing that are basically designed to boost natural muscle production and so forth. And now we've got methods for those. So, new things come along. And then sometimes you see a resurgence of old things. So, for example, cobalt in horse racing has popped up again recently.
And what does cobalt do in horses?
Well, that's a good way. Apparently, it actually doesn't actually do an awful lot. It's supposed to induce hypoxia in the body, so it increases your EPO count, so you get a higher red blood cell count at the end of it.
Which means you can carry
more oxygen. So it's similar to doing high altitude training, where you go to an area high up where there's low oxygen, so your body makes more red blood cells, and then you come back down to sea level and you can carry more oxygen. Cobalt doping improves performance in humans. It may not necessarily do the same thing in horses.
Right.
However, the idea is you boost the red blood cell and the horse can run faster. And we saw only last year there were people banned for cobalt doping in horses.
Right.
Because too much, and the horse sort of sweats, shakes, and can potentially die.
That's something that I don't often think of when I think of doping in sports. It's doping of animals.
Yes, and of course the animals can no way give consent, so
Yeah.
it's potentially a bit more serious.
Absolutely.
And a number of horses have died where they've found high cobalt levels in the blood afterwards. Yes, and you have to think if you increase the amount of red blood cells in your blood, the blood becomes thicker and more viscous. Your body has to work harder to pump it around, and if you're exerting yourself, that increases the stress, so you put a lot more pressure on your circulatory system.
And your heart especially, I imagine, to be able to pump
Yes,
that.
exactly. You're putting more stress on that whole system. And a number of very fit young cyclists have died because it's been linked to EPO use because they have this much thicker.
And coming to sort of the actual testing of the drugs, is there a consistent, I guess, sort of arsenal of tests that are used across different sports?
Yes, the tests have to be approved by the sports governing body, and they have to be proven over a period of time. So you can't actually just invent a new test, for example, then go and use it in a court of law. It has to be approved, and it has to be tested a number of times. But if I want to test for EPO in a cyclist, it's the same test that you would do for a footballer or a sailor or a football player or whatever it is.
All right, so everybody knows exactly what the tests are and how they work. everyone's on the same page about that, or is there some sort of secrecy that that the World Anti-Doping Agency can have?
Well, it's not really, because you have to, if you're going to sue someone or potentially say you can no longer race, it's a legal system, so you have to have it easy and out in the open. And if you go on to say the American Anti-Doping Agency site, they've got really good information about how the sample is taken, what happens to it after it's taken, what the system, what test is used. If you look into it, it's not too hard to find that information. If you're not a chemist or scientifically trained, some of the jargon might be a bit hard to understand. But there's an awful lot of science goes on the other side, on the cheating side. Stephen Dank was in the papers again just a couple of weeks ago, allegedly, he was about to spill the beans on what had been going on. So it's all a bit of as you say, a bit of a catch-up sometimes. You get some scientists working to detect it and some scientists working to create new things that can't be detected.
It seems that the testing is the best that it's ever been. So, I mean, how is it that the athletes are still evading drug testing? I know with the Russians it involved intricate passageways and people swapping urine samples and that sort of thing. Does it have to be like that, or are there any other sort of favourite stories of yours for how people have sort of evaded drug tests?
Oh, yes. Well, the good one was using washing powder in urine samples, for example. So if you were after testing for protein levels, which might be a marker of EPO use or something like that, what they used to do was, what cyclists allegedly did, was you'd take some washing powder or biological washing powder in particular, which has proteases, which are protein-degrading enzymes in, and that just looks like a white powder, which cyclists might have, to keep their hands dry, for example. A lot of them use chalk to keep their hands dry if they're sweating. You would basically lick your finger, dip it in the enzyme, which you'd have secreted somewhere on your body, and then you'd have to urinate over your finger into the collection cup. And then that would break down all the protein in the urine sample.
Yeah. So then they would be looking for one particular type of protein and it wouldn't be there?
Yes. And they actually spotted this form of cheating by someone realised there's no protein at all in the urine sample, which would be, indicate the person was very ill indeed. Because, once they saw that, they realised that someone had put two and two together and worked out what had been going on.
So there is this sort of catch-up that's always being played. Do you think it's just going to become part of the sport, taking drugs and testing for drugs? Do you think there's ever going to be a solution?
I doubt it, because there's so much money involved, and the differences between first and second place at the moment, there'd be thousands or millions of a second, but nobody remembers who comes second. So as long as there's pressure and money in the system, there's always going to be pressure for people to do something to get the edge on, the competition.
Well, that's all we have time for today. Thank you so much for coming in and telling us a little bit about what is happening in the world of performance-enhancing drugs, especially in the lead up to the Rio Games. So thanks so much, Ollie.
No, thanks for having me.
That's all we've got time for on this episode of Lost in Science. Thanks for tuning in and joining us. Lost in Science is recorded at the studios of 3CR in Melbourne and broadcast across Australia on the Community Radio Network with the financial assistance of the Community Broadcasting Foundation. If you want to talk back to us, you can get in touch. We have a Gmail account, lostinsight@gmail. You can also find us on Twitter and on the Facebook. And if that's not enough Lost in Science for you, you can always tune in again next week, where the team will once again get Lost in Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.